This tutorial is all about critical points and Lagrange multipliers. So we're going to work through, a couple of problems, a few problems. We'll try to refresh our memory from lectures on the material covered, and if we have a little bit of time left over, then we can talk about the class test 1. Yeah? So I'm just going to choose a couple that I've sort of solved. Essentially, my aim here is to cover one question about the critical points, one question about max and min on closed and bounded regions, and also one question on the Lagrange multiplier. So that pretty much covers everything. Okay, so I'm going to start with 81D. 81D. Anyone done it? Anyone done all the questions this week? Yeah? Nick, you have? Huh? So, essentially, we want to find and classify the critical points of all these functions. So I'm just going to choose D. No real reason. I'm just... that's just the one I chose. So our function of two variables is defined in the following way. And we're asked to find and classify the critical points. So what I mean by that is, okay, certainly go through and find where the critical points occur, but also classify them. Do they lead to a local min, a local max, or something in between, this so-called saddle point, kind of like a point of inflection? So what's going through our brains here? Well, let's realise that the critical points of F occur when, anyone remember? Yep. 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 So the first derivative test tells us that if f has a critical point, then it must satisfy these two equations, df dx equals 0 and df dy equals 0. Okay? So let's go through, calculate these partials, and we've got two equations and two unknowns. Solve for x and y, right? So f sub x is going to be something like 2x plus y plus 1 equals 0. That's going to be your f sub x. And f sub y, that's going to be x plus 2y minus 1 equals 0. Two equations, two unknowns. They're just pretty simple equations, so we can solve those. Okay. So I've solved them by elimination. So what I've done here is I've made x the subject over here and then plugged that back into the first equation. So just with a little bit of algebra, I can solve for y. And according to my calcs, I get y equals 1. Now I can back sub that value for y into either of these equations and come up with the x value. Okay, again, according to my calcs, you get something like this. So, our critical point, it appears there's only one of them. Remember, sometimes these functions can have lots of critical points. But in this case, it's pretty simple. The critical point is at -1, 1. All right, so nothing too fancy yet. The next part of our challenge is to classify this critical point. Does this critical point lead to a local max, a local min, or something in between, a point of inflection? Anybody know how we might do that? Second derivative test, right? So everyone forgets it, so here's one that I've just brought along with me to refresh your memory. So forget about this is just a summary. Second derivative test involves looking at, in this context, the second derivative of f with respect to x and the sign of the discriminant. Okay, remember you can think of the discriminant as something like a special determinant of a matrix involving the second partials. Okay, so let's go through and calculate f sub xx and the discriminant, and then we'll see which one of these cases we have. So I guess that's part 1. Part 2, classify our critical point by the second derivative test. So for the second derivative test, of course, we'll need, oh, that's right, second derivatives. So let's calculate all these second order partials and put them in. Let's consider. All right. F sub xx. Well, if f sub x is up here, f sub xx is just going to be 2. Now, it doesn't matter where you evaluate that second derivative, it's always going to be positive. Okay, so usually what you would do now is put, -1, 1 into here, but there's no x's or y's, so it's always going to be positive. So we realise that this is always positive. So it looks like might be the first case, but let's test. We also have to test the discriminant, okay, because it could be the third case or the fourth case. We don't know yet. Okay, so let's look at the discriminant. So f sub xx is 2. We just calculated that from above. F sub yy, what's that going to be? It's going to be something like 1. Oh, sorry, no, f sub yy is going to be something like 2, sorry. F sub xy, well, differentiate that with respect to y. I'll get something like 1. And I want to evaluate this at our point of interest again. It doesn't really make a difference because we've got constants here. So it's going to be positive or negative. Well, it's going to be positive. Okay. So we've got this case and the discriminant's positive. So via the second derivative test, we would say that f has a local minimum at this particular critical point. Okay, can you guys see up the back? Yeah. Any questions?
Yeah, why is it a local minimum, not a global?
Well, it could be a global minimum. There's nothing saying, in this test, That's a really good question. Why is... I mean, you can see the conclusions don't say anything about the global being a global maximum or a global minimum. It could be, but you just don't know.
How can you get one that's like?
Well, you might be able to. Well, to show that this was a global minimum, what you would have to do is somehow factorize this in a way where you're sort of adding together. I mean, the minimum value is 0, right? If you put -1, 1 into f, the minimum value is 0, okay? And what you would have to do in order to prove that is, I guess one way would be to factorize this in some fancy way, so you're adding together things that are squared, okay? Because, you know, square things, if you square anything, it's always greater than or equal to 0, okay? But I mean, it's a really good question on a number of levels, because what it does show you is the limitations of the second derivative test. The conclusions say nothing about the global nature of that critical point. It might be a global minimum, but you just don't know without doing something else. So that's pretty standard. As long as you can basically differentiate, solve your partials up here, equal to 0, and then apply the second derivative test, it's not too bad. Now, it's unlikely that you'll get the second derivative test in your exam. You have to recall it or remember it in some way. Okay, so the discriminant is probably the hardest thing to remember. So that's why I've said, well, you can think of it as the determinant of a special matrix. Okay, let's do one of these. Aha. Yes. Now I know that the writing's very small here. 83b. I think that's the one I've done. Yes. 83b asks you to consider a given f on a rectangle. And you're asked to determine the maximum and the minimum values of f on the rectangle. Now, I did a problem similar to this in lectures, but you were working on a disk and we were looking at, isotherms or something like this. So, firstly, let's just look at the nature of what we've got here. This is just a polynomial, right, in x and y. It's continuous, and this region here, when I draw it, is just a closed rectangle. So you've got the rectangle that includes its 4 sides and everything inside those 4 sides. A continuous function on this sort of closed rectangle must have a maximum and it must have a minimum value. So the things that we're going to calculate, they're well defined and we shouldn't have a problem calculating them. Now, let's just write down what we want to do. So we want to maximize, minimize the following f. On the rectangle, I'm going to call it omega. Okay, can anyone remember? Or has anyone done this question? Anyone? Yeah? How did you do it?
I tried it. I could only find one critical point when I differentiated.
Yep.
I
So.
wanted to go for a boundary, but I couldn't find it.
Interesting. Okay. So, with these problems, the sort of the inner monologue is the following. Okay. So, we've got some sort of. Okay. Think of this as the domain of this function. It's a rectangle. So you were right when you said let's look for critical points, but there's another element to this problem. the extreme values of our f, they occur either at critical points inside the rectangle, i.e. not on the edge, or they occur on the edge, okay, along the sort of boundary. So that's an important observation. So the extreme values, or the extrema of f, occur at critical points. Okay, by critical points I mean the points inside the rectangle, not on the edge. Or on the boundary. Okay, so let's think about the boundary for a second. Okay, so by the boundary I mean this line segment, this line segment, this line segment, this line segment. Okay, so let's do as we did in the previous example. Let's calculate the critical points first. Then we'll move on to the worrying about the values of f along the boundary. So f sub x, f sub y equals 0. So let's calculate these and solve them. So 2x minus y minus 1 equals 0, and 2y minus x minus 1 equals 0. Okay, so you've got two equations, two unknowns. Go through and I just used elimination. Now, I'm not going to do all the calculations for you because the slightly more challenging part of this problem is what happens on the boundary of our I guess it's not a square. I've been saying rectangle, it's a square. Well, a square is a kind of rectangle. Okay, so according to my calcs, you get x equals 1, y equals 1. Okay, so let's look at the value of f at our critical point. Okay, so I plug in 1, 1. Sorry, hang on. I think I made a mistake there. No, 1, 1, yeah. And the value of our critical point is actually minus 1. Okay, now we'll come back to that a bit later. So that's as long as you can solve the equations, that's reasonably easy. But what happens on the boundary? And this is actually the slightly more involved part. Okay. So this is important now. What we're going to do is just look at these 4 line segments. Right, along this line, let's just look at this line segment here, this bottom bit. You can see here that x doesn't change. That y doesn't change along here. Y is always along this line segment. Right? Up here, y is always 3 along this line segment, and x changes. Along here, y changes, but x doesn't change. And along here, y changes, but x is always 3. Now, if you just take one of those little segments, you can consider f where one of the variables doesn't change. What this means is instead of having a function of 2 variables here along these line segments, I've got a function of 1 variable. So then what I can do is just use high school calculus to calculate the maximum and the minimum values. Also remembering I need to be concerned about what happens at the endpoints. So let me show you, and hopefully you can get the gist of it. So on the boundary of omega. Now I'm not going to do all 4 cases because that'll probably take up the rest of the lesson. So I'll do one or two to get you rolling. All right, so let's just take, say, okay. So x equals 0, so I'm just concentrating on this line segment at the moment. Okay, when x equals 0 and y is between 0 and 3, so all I need to do is go up here, replace x with 0, and I'll form some function of one variable, y. Okay, so I'll get y squared minus y. Okay, so what I can do now is just use basic calculus on this h function. Where are its critical points? Where are its extreme values? Well, if y is between 0 and 3, well, I've got to test those endpoints. But I can also differentiate this, set it equal to 0, and find the turning points. So h of 0 equals 0, and h of 3 is going to be something like 6. So they're the endpoints taken care of. So at y equals a half, let's calculate what we've got here. We're going to have a quarter minus a half, which is going to be minus 1/4. Okay, so we've got that value, that value, that value. So what's the maximum value of our function along this particular line segment? All we do is we compare these 3 values. Which one's the maximum? Which one's the minimum? Well, the minimum value is minus 1/4. The maximum value is positive 6. So along this line segment, our function has a minimum value of minus 1/4 and a maximum value of positive 6. How does that compare with what we've just calculated in the interior? Well, that's greater than that. That's also greater than that, and so well, that doesn't come into play. So essentially, what these problems come down to is computing all these local max and mins and then comparing them. That's all it is. Which one's the biggest value? Which one's the smallest value? Okay. So the maximum of f is 6, and the minimum of f is minus 1/4. Okay, this is just on the line segment. I'm not saying anything else. Okay, let's choose a different line segment. In my solution, I've chosen this one here. So what would the restriction there be? It'd be x equals 3, y is between 0 and 3, right? So So here, let's form a function similar to what we had here, but instead you're going to get a 3 and a y there. So you go up here, plug in x equals 3, and you'll get a new function. Okay, so I'm going to slightly abuse the notation by using h again. Okay, if you don't like it, then you can just change it. Okay, so if you put in x equals 3, you'll get this. So now I've got a function, another function of one variable. Let's look at the max and the min, look for turning points, just by using what we know from school. I'm not going to put all the working in. So the maximum, according to my calcs, again, you get 6. And the minimum is going to be 2, and you'll get another value somewhere in between those. So you go through and do the other 2 segments. You don't have to at this stage. Yes? Up here? Let me have a look. So sub in 3. No, I think I'm okay. Yeah. Okay, so let's now you've got to compare those with what you've got over here. Okay, so it's all a whole big comparison now. So the other cases, I'm pleased to announce, will give you very simple, well, actually identical answers to the ones I've just computed. It's because of the structure of f and the sort of sides, again, being very similar to the first 2 cases. So the other line segments give the same or similar answers as the 2 we've dealt with. Okay, so go through and check those. So all we have to do now is, once we have all those, there's no real new information to add. All we have to do is look at what we've got here. What's our, so here, so here, 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 here. Which one's the maximum value? Which one's the minimum value? Well, the maximum value is positive 6 in a few different places, and the minimum value is minus 1. So over that whole square, the maximum value is going to be positive 6, and that's achieved at a few different points. And the minimum value is going to be minus 1. Okay, so the type of notation, so the maximum of f on our square, it's positive 6, achieved at a few different places, and the minimum of f on our square is minus 1. Now, I've got to say, if you've got a question like that in the end session exam, I'd be unhappy because it would take you a long time to solve it. I probably spent 15 or 20 minutes solving that problem, right? So I guess what I looked for in this problem was shortcuts. I worked out that you only had to do 2 of the edges to get the other 2 edges, the maximum and minimum values. Okay, of course you can grind through it, no problem. But yeah, you want to work. I guess you want to work smarter, not harder. 84. Find the points on this curve that are closest to the origin. Anyone done it? Okay, so maybe you can talk us through it as we go. How does that sound? So this is 84. So we want to, what's the function we want to minimise here? Right, so we could either have root x squared plus y squared, or just forget the square root sign because it's easier and sort of seems to make more sense to work smarter, not harder. So we want to minimise this function subject to our constraint. Okay, so what do we do? Yep, let's write down the Lagrangian function. So we're going to let our Lagrangian just be f minus lambda g. We're going to look for the critical points of L. So to find the critical points, of course, we want to differentiate, set all the derivatives equal to 0. So find the critical points of this Lagrangian function, L. So the critical points of L by solving L sub x equals 0, L sub y equals 0. Now, sometimes these as we've seen, sometimes these equations are easy to solve and sometimes they're not. So let's go up here, calculate our partials. We're going to get x plus 2y. We set them equal to 0. Now, we're sort of in a bit of a bind now. We've got these two equations down the bottom. Don't forget, we've also got our constraint equation, so we've kind of got 3 equations. But how did you solve these equations down here? I'm a little confused.
I don't know if you did it the wrong way, but in the first one,
Mm-hmm.
I set y equals 2x over lambda minus 2x.
Mm-hmm.
So for lambda.
Okay.
And then I got 2 values for lambda, and then I put that into my first equation
Yep.
for y.
Yep.
And then I got the value of x.
Okay, that's certainly, I have no problems with that solution at all. It isn't the way that I did it. I guess in at least one of the problems that I've solved in lectures, there was a method where I multiplied the first equation by x and the second equation by y, and then eliminated some sort of eliminated as much as I could out of them. Now that won't work every time, but it's not a bad thing to know. Yeah, you're right. Okay, so just scratch that. Let me just adjust that. Yes, that'll do it. Yep. So you should get something like this. So multiply the first one by, yeah, this is good. Aha, very good. So now what I'm going to, as you can see, I've got a lot of the same terms. The first term in both equations are the same, and if I sort of pull this out, I've got a lambda 2xy in both equations. So what I can do is just take one equation away from the other, and then I'll get something like something involving lambda x squared and y squared with a common factor of lambda. So let's call this A and B. And let's call our constraint equation C. So in terms of A and B, subtracting one equation from the other, doesn't matter which one, we're going to obtain the following. There's a common factor of lambda, and we get this type of equation. Now, so what? Well, the point is we're now in a position where we can make some sort of conclusions about lambda, x and y and their relationship to each other. So what do you know from this bottom equation? You know either lambda is 0 or y equals plus or minus x. Okay? Lambda equals 0 or y equals plus or minus x. So there's three cases to discuss. The case lambda equals 0, the case y equals x, the case y equals negative x. So in many of these cases you can rule out these situations just by seeing whether it makes sense. So who can tell me why can't lambda equal 0? Anyone know? Why can't lambda equal 0? Well, let's look at what equations we have. If lambda equals 0, right, then up here we'll get x equals 0, y equals 0. Now, if you sub x and y equals 0 in here, it's not going to hold. Okay, this equation cannot hold for the case lambda equals 0. Okay? But so ignore the case lambda equals 0. What about the other two cases? Say y equals positive x. Well, if y equals positive x, I can go back to my constraint equation, just replace y with x, and I'll get some sort of equation involving x squared. Okay, so I'm going to get x squared plus x squared plus x squared equals 2. So then I'll get x equals plus or minus root 2 on 3. Now, if x equals plus or minus root 3, and we know that y equals x, then y's got to be the same as x. In the last case, when y equals minus x, just do the same thing. Use the constraint equation again. Okay, so we're going to get y equals minus x, so we're going to get x squared minus x squared plus x squared equals 2. So again, you've got an equation here involving x squared. Okay, almost there. So when I put the minus on top of the plus, I mean, when x equals positive root 2, y equals minus root 2. When x equals negative root 2, y equals positive root 2. That's what I mean. If you don't like that notation, again, you can use your own. So our points of interest we've got 4 points of interest. Okay, so here they are. There we go. So all we have to do now is go back to our F, evaluate them at points A, B, C, and D. What's the biggest value? What's the, we're interested in the minimum value, right? So we want to put all these points into F and look for the minimum value. So the value at these points are the same, and the value at these 2 points are the same. So which one's the smallest? Well, this value here. Now, I've run out of time, but if they ask you for the minimum distance, all you would do is take the square root of our values, because we've been using the square of the distance function.